Hey guys, in this video we want to do the following question. So suppose we have a graph G which is k-connected. So let's imagine where the graph G is over here and it is k-connected. And suppose we have another graph G prime which is obtained from G by adding a new vertex Y with at least k neighbors in G. So this is how we can visualize the graph G prime. So we have the graph G, and then there is a new vertex Y, okay, which is outside G, such that it has at least k neighbors inside G. All right. So we construct the graph G prime from G by adding this new vertex Y together with at least k neighbors. So this is called the graph G prime. Now our task is to prove that the graph G prime is also k-connected. Right? The graph G that we started with is k-connected, and we want to show that by using this construction, the graph G prime is also k-connected. Alright, before we proceed to the proof, here's one observation about the graph G and G prime. Namely, if we delete the vertex Y from the graph G prime, we get back the original graph G. Okay, let me box this up and we're going to use this later on. To show G prime is k-connected, it's enough to show that any vertex card of G prime must have size at least k. So let me write this down. The goal is to show that if we start with any vertex card U, of the graph G prime, then the size of U must be at least k. Okay, so basically this is the definition that the graph G prime is k-connected. Well, we're going to consider two cases depending on whether the vertex Y is inside the set U. For the first case, let's assume the vertex Y is inside U. Well, by the definition of U, since it's a vertex card, we know that the graph G prime having U deleted is disconnected. Right, this is nothing but the fact that follows from the definition of a vertex card. Now, to determine the size of U, we're going to look at the graph G minus U. Okay? What is G? Remember, G is actually G prime with Y deleted. So I'm going to replace G over here by G prime with Y deleted. So let's see what is the resulting graph. We have a graph starting from G prime, followed by a deletion or the removal of the vertex Y, and then with a further removal of the entire set U. But Y is inside U. Okay, this is the case we're considering. So G prime deleted Y deleted U is just G prime deleted U. Right, because Y is already inside U. So these two graphs must be the same. Okay? And so from here we conclude that G minus U is disconnected. Remember, G prime minus U is disconnected. So the conclusion is the vertex U is a vertex card of G. Okay? So we started with a vertex card of G prime. And the conclusion here is that U is a vertex card of G. But what is the graph G. A graph G is a graph which is k-connected, which means any vertex cut must have size at least k, right? K-connected means the connectivity is at least k, but connectivity is the minimum size of a vertex cut. And since U is a vertex cut, the size of U must be at least k, since G is k-connected. So we have proved that the size of U is at least k in this first case. Let us now move on to the second case. Well, in the second case, we have the vertex Y being not inside the vertex cut U. So this is how the graph G prime will look like. And let's say this is the vertex cut U. Then having U deleted from G prime, the graph will be disconnected. So let's say this is one of the component after deleting U. Let's call it H. And let's say there's another component after deleting U from G prime. Let's call it H prime. There could be other components because when a graph is disconnected, it will have at least two components. So let's say these are the two components. I mean, one of those two components after deleting U from G prime. Well, where is the vertex Y? There are two cases, or there are two possibilities. Either Y is by itself one component after deleting U, or Y can be connected to somebody else in one component after deleting U. Let me draw the pictures of these two possible cases. So in the first case, we have Y being joined to vertices in U, because Y is going to be by itself as a component after deleting U. Okay, maybe the other component is called H over here. Right. The other case is that the vertex Y is joined to some of its neighbors after deleting U. Sorry. This should be the set U. And maybe the component H is over here again. So the vertex Y will be in one component, let's say H prime, together with some of its neighbors. Now there might be some neighbors of Y which is inside U. We wouldn't know how many they are. This could be empty though. There may be none of, if there's no neighbors of Y inside U, then there must be some edges from U to some other vertices in H prime. Okay, so a generic picture will look something like this. Anyway, let's consider these two cases and see what happened to the size of U. Right. In the first case, it's quite easy to see that the size of U is at least k, because you see all the neighbors of Y is inside U. So maybe this is the first neighbor, this is the second neighbor, and so on. But remember, there are k neighbors of Y by construction. So immediately we can conclude that the size of U is at least k, since Y has at least k neighbors. And this will settles the case for this particular configuration. All right, let us move on to the second picture on the right. Now this time, as before, we are going to look at the graph G with U deleted. And let us look at what is the picture of this graph. Remember, G is the graph G prime minus Y. Okay, that was our observation in the beginning, right? G prime minus Y is G. Okay, so this is G. and then we have the vertex cut u. Now we're going to combine u and y together. So we're going to think of this as the graph G prime having the set u union y being deleted from G prime. Let us now visualize the graph G prime having u and y deleted. Well, so if we delete u together with y, then the graph is going to fall into at least two components, right? One of which is h over here, and then another component, right, containing some of these neighbors of y in the component h prime. So this is where it differs from the previous case, right? Because in the previous case, y doesn't have any neighbors in the component h prime because y itself is the component h prime. But over here, you see, we have some other vertices giving us at least two components after deleting u and y. So this means u is a vertex cut of G because the graph is disconnected upon deleting u from G. But remember, G is k connected, which means the connectivity of G is at least k, and therefore the size of u must be at least k, right? The connectivity is the minimum size of a vertex cut, and u is a vertex cut of G, so the size must be at least k, since G is k connected. And we are done. We have proved that the size of u is at least k in the second case. Hence, the result follows. All right.